In a previous video we looked at the stress concentration factor as a parameter to describe the influence of the geometry on the fatigue performance of a structure. We looked at what causes a stress concentration. I gave you a definition, but that definition related to a notch in an infinite plate, because then mathematically the stress concentration can be well described. But how does that work in practice? Because in practice we work with finite dimensions of a structure. And in this video I want to spend some time on that. We should realize that the stress concentration factor does not capture all the aspects related to the geometry. We may have two different cases, for example two circular notches with different diameters in plates with a different width, that in the end have the same stress concentration factor, but simply because the size of the high stress region in the notch is different, the fatigue performance may still be different. So how do we cope with that in practice? Well, let's have a look at that. A circular notch in an infinite plate has a stress concentration factor equal to 3, as we have seen before. And now the question is, what if the plate has a finite width? What is then the stress concentration factor? Well, that can be illustrated with a graph here on the right hand side. The stress concentration factor equal to 3 for an infinite plate is reducing once the width of the plate is becoming smaller. And this relationship illustrated here is given by the equation of Haywood, which says that the stress concentration factor of a circular hole in a plate with finite width is given by this equation. In other words, the stress concentration factor reduces if the width becomes smaller. Now that may seem counterintuitive, because if the width becomes smaller, the nominal stress will increase. So how does that work? Well, let me illustrate it with this example. We have an infinite plate with a circular hole, and the corresponding stress concentration factor is given by Kt is 3. Now we can make a distinction between the nominal stress, as I have given before in the definition, the peak stress divided by the nominal stress, but we also can define the gross stress concentration factor, which is the peak stress divided by the applied stress. Now if I reduce the width of this plate, then obviously both the nominal stress and peak stress go up. That means if I divide the peak stress by the increasing nominal stress, the effective stress concentration factor, which is the nominal Kt, is reducing. But if I divide the increasing peak stress by the original applied stress, then obviously the gross Kt is increasing. So if I plot the Haywood relationship, which is this blue curve starting at 3 for an infinite plate and reducing once the width becomes smaller, then the corresponding Ktg, or the gross stress concentration factor, is increasing and given by this equation. Now you can recalculate one equation into another simply by applying the equation given here. Now if this circular notch is an elliptical notch, then obviously the relationship is similar in trend but different in magnitude. So depending on the long and short axis of this ellipse, we start with a different stress concentration factor, and then the nominal stress concentration factor will decay once the width becomes smaller, and the gross stress concentration factor correspondingly will increase once the width becomes smaller. Now if you look at handbooks or textbooks that give you relationship for this, you can immediately recognize that this is a very empirical description. You have all those empirical relationships based on the dimensions of A over B. You can find the corresponding constants C1 to C4 and you fill in the equation, you can calculate the stress concentration factor. That basically means you either work with those empirical relations or you simply look it up in a graphical chart, as you can find for example in a textbook like Peterson. So let's take a practical example. Let's do this exercise. We have an elliptical notch in a finite plate, as illustrated here. So the long and short axis of this ellipse are given by A and B. The radius in the notch root is 5 mm and the plate width is 100 mm. So how do we calculate the stress concentration factor for this one? Pause here the movie and try to find the answer yourself. So what is the best way to go forward? Well, we know for this given ellipse in an infinite plate that the Kt is equal to 1 plus 2 times the square root of A over rho, which in this particular case is 5. Now for a circular hole in an infinite plate, we know that the stress concentration factor is given by Kt is 3. So what we can do as a first order approximation is assume that for the finite plate dimensions, the same ratio of the ellipse over circular KT applies as to the infinite one. Hence, with the equation of Haywood, I can calculate the stress concentration factor for a circular notch in a plate of 100 mm width. Assuming that the diameter of the hole is 2 times A, then Haywood tells me the stress concentration factor is 2.2. So assuming the same ratio of elliptical over circular notch for infinite, I can take the ratio of 2.2 divided by 3 times the KT of 5, and that gives me a stress concentration factor of 3.7. Okay, this is an approximation, but how close are we? So if we look up the chart in Peterson, for example, and for the given dimensions of this problem, and we look up what the stress concentration factor is supposed to be, then we are fairly close. Although this is an approximation, it's a very good approximation. Now we have seen that the stress concentration factor describes the influence of the geometry and is independent of the stress applied. However, it's not independent of the load case applied. So let us look at the role of the load case and the geometry on the value of the stress concentration factor. Let us first compare these three examples. We have a circular notch in a plate with width 100 mm. Then with the equation of Haywood we can calculate that the corresponding stress concentration factor is 2.25. If we add holes with a smaller diameter on both sides of that notch, we effectively reduce the stress concentration factor to 1.8. Obviously, if we replace those three holes by an ellipse with a long axis equivalent to the distance between those holes, then the stress concentration factor is further reduced. Now here the stress trajectories are being illustrated because the key thing is that we should identify that the stress concentration factor effectively describes how condensed the stresses locally are at the notch root. So by adding those two additional holes on both sides of the larger notch, we effectively push the stress trajectories outward and we reduce the stress concentration at the notch root of this larger diameter hole. You can see that with the ellipse something similar is obtained and hence the stress concentration factor is further reduced. Another example is this flat plate with two notches on both sides. So in the notch root the stress concentration factor is 2.55, and we can illustrate with the stress trajectories that indeed at the notch root on both sides a stress concentration is present. Now if we remove a piece of material and we should redraw again the stress trajectories, we would identify that the density of stresses near the notch root is reducing. So hence removing this part of the material, we effectively bring down the stress concentration factor. If we then also remove material further upstream, then we can even bring down the stress concentration further, simply because less stress is concentrated at the notch root. So we can play with the geometry in order to change the value of the stress concentration factor. But now let's assume we have a similar notch geometry and we change the load case. So we have the sheet in tension with the notches on both sides, then the stress concentration factor is given by 2.55. If I now have a rod with a diameter equal to the width of that plate, and I have a groove in the circumference which has the same radius as the notch in the plate, what I will find is that in case I apply tension, the stress concentration factor is less than 2.55, actually it's 2.23. If I take now the same rod and instead of tension I apply bending, the stress concentration goes down further. How does that work? So I don't change the geometry, but I change the sheet to a rod. I change the stress concentration factor. And if I change tension to bending on the rod, I further change the stress concentration factor. What you should try to do for yourself is illustrate the stress trajectories, and you will identify that indeed they will be different. In any case, if we change the load case, even though we are talking about the same geometry, the stress concentration factor will be different. So if we have a fillet here with a fillet radius, we will have two different curves to illustrate the effect of tension and bending on the effective stress concentration factor. Changing the load case changes KT. The Haywood equation for an open hole describes that the KT of 3 decays to a lower value if the width becomes smaller. But if I now apply a pin and I load the hole, then the stress concentration factor will be higher, simply because the load that I introduce by bearing is passing by near the notch root and increasing the stress concentration factor significantly. The same diameter, the same width, different load conditions, it gives a different stress concentration factor. Let's take this example. We apply bearing pressure in the circumference to this flange, which is in equilibrium with a tensile force on this side. Then depending on the radius, we may change the stress concentration factor. But we can also change the stress concentration factor by keeping the radius the same but increasing the thickness of the flange. We can even halve it. Obviously, if this would be purely tension loading, then the stress concentration factor would be reduced further. What it illustrates is that the load case, together with the geometry to which we apply this load case, defines the stress concentration factor. So as a designer, we have freedom there.